In this next example, we're going to be doing essentially the same problem, but here we're going to incorporate in the cost of the fencing. A fence must be built in a large field to enclose a rectangular area of 15,625 square meters. One side of the area is bounded by an existing fence. No fence is needed there. Material for the fence costs $2 per meter for the two ends and $4 per meter for the side opposite the existing fence. Find the cost of the least expensive fence. Now that we understand that we have to work with the cost of the fencing here, and we're trying to find the least expensive fence, I'm going to have to be minimizing cost. So I'll start by writing out my three parts of the fencing. The existing fencing is here in black. So the only difference in this diagram is before I went ahead and I had a river along this other side. Just to be different, I'm going to label X horizontally and Y vertically, and it'll change how we do the problem a little bit, but it still is fairly straightforward to solve. So the information that we're given is that the area, X times Y, is 15,625. And now we need to talk about the cost. To get the cost, we need to notice that there's one part of the fence that's X long, and that piece is $4 per meter. And there are two pieces that are Y long, and those are $2 for each piece. So our cost is going to be 2 times 2Y, so the $2 times 2Y of fencing, plus $4 per meter times X meters of fencing. This has two variables. This is going to be the thing that we're going to have to eliminate one of the variables from. So the way I'm going to do that is I'm going to take my area equation up here, the xy equals 15,625, and solve it for one of the variables. I'm going to solve it for y. So what I get is y equals 15,625 divided by x, and now I'm going to put that into the cost equation. That gives me c equals 4 times 15,625 over x plus 4x. I've gone ahead and multiplied the 2's together to give me that 4. Now I'll multiply the 4 times the 15,625 because I'm thinking of that as 4 over 1. So I multiply top times top, bottom times bottom, and that leaves me with 62,500 over x plus 4x. To make it a little bit easier to take the derivative of, I'll move that x upstairs and think of the 1 over x as x to the minus 1. So what I'm going to take the derivative of is 62,500 x to the negative 1 power plus 4x. And all I need to do here is use the power rule. So when I take the derivative of the x to the negative 1, it gives me negative 62,500 x to the negative 2. And the derivative of the 4x is simply 4. I'll bring that x to the negative 2 downstairs as an x squared. So what I now have is negative 62,500 divided by x squared plus 4. And now I need to find the critical point of that. To find the critical points, I need to set negative 62,500 over x squared plus 4 equal to 0. I'll also note that this is going to be undefined at x equals 0 because this fraction will make no sense there. But to go ahead and find the critical point, I'm going to move that negative 62,500 over x squared to the other side by adding 62,500 over x squared to both sides. That leaves me with 4 equals 62,500 divided by x squared. If I multiply both sides by x squared, that'll clear out that fraction, and it leaves me with 4x squared equals 62,500. To isolate my x squared, I'll divide both sides by 4. That leaves me with x squared equals 15,625. And then I'll square root both sides. And that leaves me with x equals 125. The x could also be negative 125, but of course I've thrown that out because it doesn't make sense to have sides here that are negative values because they're lengths of fence. So I've gone ahead and made my number line for the first derivative. I've put on the critical point where it was equal to 0 at 125, and I've also labeled the point at 0 where it was undefined. Now I'm going to test in these places here, and so I'm going to pick 100 and 200, and those need to be placed into C prime down here. When I put 100 in place of x, I get a negative number. When I put 200 in place of x, I get a positive number. So what that tells me is this function was decreasing, so it was dropping down, it had a critical point, and then it went back up because on the right-hand side it's increasing. You might be a little bit worried about this point right here, but remember, in the cost function we had originally, it had a divided by x, and this actually corresponds to an asymptote. So what that's showing is that it drops down from the asymptote before it hits the critical point, and then it goes back up. That's telling me that this is a relative minimum, and since it was up high on either side, it's also an absolute minimum. I can verify a little bit further by taking another derivative of negative 62,500 x to the minus 2 plus 4, and that gives me 125,000 x to the minus 3. Simplifying that gives me 125,000 divided by x cubed, and if I were to put 125 in place of x here, I'd get a positive number, and a positive number means that it's concave up. So that means our area is 125 by 125 meters, and I can get that other 125 using my area expression up here. And the cost then is going to be C equals 4 times 125 plus 4 times 125, or $1,000.